I'd like to thank the organizers of this meeting for the invitation to present this talk today. Also, I wish to thank all of you online attending this meeting and attending my talk. So today, I'm going to talk about how the nanomorphology impact magnetic hyperthermia performance. So here is my outline for today. I briefly will comment you about magnetic hyperthermia, what that means, and then I will shortly introduce the magnetic hyperthermia basics and some details of the instrumentation design, and then I will skip to the challenging and targeting of magnetic hyperthermia. So how to go around the challenge. And so I will present some possible solutions, like for instance, the instrumentation and the magnetics design. Then I will show you some interesting results about magnetic hyperthermia in tumor therapy. And the last topic of my talk will be some comments about the so-called Box-Lucas model. And then conclusions about my presentation. So as you can see on the lower part of my slide, there is a very strong statement made by Hippocrates for 60 to 370 AC. So Hippocrates is actually this Hippocrates is Hippocrates the second, and this is the father, considered the father of the modern medicine. So as you can see, this statement is written in Latin, and likely most of you may not read Latin. So here in my next slide, I show you the translation from Latin to English. And this is the basics of magnetic hyperthermia. So it says, those diseases which medicine do not cure, knife cures. Those which knife cannot cure, fire cures. And those which fire cannot cure are to be reckoned wholly incurable. So as you can see, is a very strong statement. And this is the first report about magnetic, about hyperthermia. So hyperthermia in the modern time, in the last 20 or 30 years, has been performed using nanoparticles. And there are two ways to perform hyperthermia today. One is the magnetic hyperthermia, using magnetic nanoparticle. And the other one is the optical hyperthermia, using specifically some metal nanoparticles like gold and silver. What is the difference here? So magnetic hyperthermia is based on the magnetic hysteresis curve. However, the optical hyperthermia is based on the surface plasma resonance. They are quite different mechanisms. What is a very important difference between magnetic hyperthermia and optical hyperthermia? So magnetic hyperthermia allows you to promote remote manipulation of the magnet nanoparticles. And in addition, it allows you to perform remote heating. So you can apply external AC magnetic field. That is what is the meaning of remote heating. On the other hand, the optical hyperthermia, it does not allow you remote manipulation of the metallic nanoparticles. And likewise, it does not allow you to perform remote heating. Why is this? Because it requires application of a laser light, and the penetration of the laser light in the skin, in the body, is quite limited. Maximum, perhaps 7 to 8 millimeter, depending on the wavelength. So it seems right at the beginning, the magnetic hyperthermia has more capability to handle the hyperthermia than the optical hyperthermia. So let me briefly comment about the basics of the magnetic hyperthermia. On the left-hand side of my slide, you can see a sketch of spherical nanoparticles, and they are magnetic. You can see the magnetic moments on the magnetic nanoparticles. If there is no applied external field, the net magnetization is zero. Why is that? Because the magnetic moments of the nanoparticles, they align randomly, and so they cancel each other. However, if you apply an external magnetic field, all the magnetic moments they align with the external field, and then the net magnetization is not zero. However, if you shut off the magnetic field, the magnetic moments will relax back to the random orientation. And that relaxation, it takes time. And there are two mechanisms of relaxation. One is called the neo-relaxation time. And neo-relaxation time is the relaxation of the magnetic moment inside the crystal structure of the magnet nanoparticle. On the other hand, the Brownian relaxation time on the right-hand side here, it means the relaxation, the randomization of the magnetic moments by the randomization of the orientation of the nanoparticles themselves. So it means nanoparticles, they turn around until the orientation of the magnetic moments are randomly placed in the space. So actually, the net relaxation time is a combination of neo-relaxation and Brownian relaxation. So the net relaxation time scales with the neo-relaxation and Brownian relaxation, like I can show you in this expression. Actually, the frequency of the net frequency of relaxation is the Néel frequency plus the Brownian frequency of relaxation time. Okay, so bearing in mind that we have these two relaxation mechanisms, we can understand the process of generating heat. So let's say to generate heat, you have to apply an external AC magnetic field. When you do this, the magnetic moment try to follow the external applied AC field. And there is a very important relationship between the net relaxation time and the typical time of changing the AC magnetic field. So if the typical time of reversal of the external applied field is higher than the relaxation time, so it means that the nanoparticles have enough time to follow the applied external field. And you see a hysteresis curve like the upper plot here. However, if the typical reversal time of the external field is smaller than the typical relaxation time, the hysteresis curve just open up, like I can show you here in the lower part of my slide. So the hysteresis has a cycle with an effective area inside the cycle. And this area provides you the mechanism of the magnetic hyperthermia. The area here scales with the amount of heat the nanoparticles can deliver to the site where they are located. So this is the basic, this is the basic mechanism of magnetic hyperthermia. But remember, this area is a result of the net relaxation time, which means a combination of Néel and Brownian relaxation time. So the heating can come from the Néel mechanism, or it can come from the Brownian mechanism. The Brownian mechanism is the mechanism that the particle rotate itself in the medium. So keeping in mind and focusing on magnetic nanoparticles to promote magnetic hyperthermia, the first aspect is the remote manipulation, which means you can use gradient of magnetic field, external gradient of magnetic field, as pliers. So you can move around the nanoparticles, the magnet nanoparticles, and eventually you can locate them in a special spot, the one where you want to promote heating. So, and the force applied to the magnet nanoparticles due to a gradient of magnetic field scales with the DC susceptibility, and also scales with the size of the nanoparticle, the volume of the nanoparticle. And the heating is promoted by the amplitude of applied external field, the frequency, the AC susceptibility. So the heating, how much the temperature is increased due to the magnetic hyperthermia, scales with all these parameters. So the time, delta T, is the time that the AC field is applied. Here we have the amplitude of the applied external field square, the frequency, AC susceptibility, and inverse of the specific heat of the medium. So these two relationship gives you an idea how to control and how to manipulate the magnet nanoparticles and place them to the right site where you want the magnetic hyperthermia effect takes place. So remember, the heating depends on the time you are applying the external field, depend on the amplitude of the external field, and depend on the frequency, which means these three parameters actually are instrumentation parameters. On the other hand, the AC susceptibility, it is a parameter related to the magnet nanoparticle itself, and the specific heat depends on the medium. Okay, so in terms of instrumentation design, we can manage the heating. Here is again the expression of how much you can increase the temperature when you perform magnetic hyperthermia. So you can modulate this heating by doing electronics, which means the time you applied the external AC field and the amplitude of the AC field and the frequency of the AC field. This is the instrumentation parameters you can control. Of course, you can extract the temperature, which is a very important experimental parameter. so you can control how much you are heating your sample, but also it depends on the magnetic characteristics of the nanoparticles you are using to perform the magnetic hyperthermia. In particular, it depends on the specific heat of the medium and the nanoparticle, and the AC susceptibility of the nanoparticle. So you can control the heating. At the end, you can control the heating by controlling your uh, instrumentation parameters and also controlling the particular characteristics of the magnetic nanoparticles. Okay, here is one example how the heating of the nanoparticles, how you can measure the heating of the nanoparticles. So this experiment is reported in this paper. This is a group from Dr. Hilger in Jena in Germany. So what they did, they use a new mice, they plant a tumor on the backside, and then they injected magnetic nanoparticles in the tumor. So they could measure the temperature of the tumor and the temperature of the body. And then they plot here the temperature of the tumor. So it as a function, so temperature here is in Celsius, as a function of time that the AC field is applied in seconds. So they go up to about 5 minutes application of AC magnetic field. And you can see the temperature of the body is almost constant, a little bit lower 30 C. However, the temperature of the tumor goes up close to 70 C. So here is a very important border. And the big challenge of magnetic hyperthermia is to keep around 43 C. Why is that? This is a very important border in magnetic hyperthermia. If you are using magnetic hyperthermia as a cancer therapy, so around 43 C, you perform what they call thermal sensitization, which leads the apoptosis of the tumor cells. If you go higher than 43 C, and the higher you go, the more strong the process is. So you go to the thermal ablation, which leads to necrosis. Okay, what is the main difference between necrosis and apoptosis? So the thermal ablation leads to necrosis, which means the disruption of the tumor cell membranes. On the other hand, if you keep around 43 C, and then you go apoptosis, and apoptosis is thermal sensitization. What it does, it damages the mitochondria. And once the mitochondria is damaged, it triggers the apoptosis of the cell. So the big difference is in the thermal ablation, you induce in the body a very strong reaction from the immune system. So, and this strong reaction is not desirable. So the big challenge of the magnetic hyperthermia, as far as the cancer treatment is concerned, is to keep the temperature around 43 C and then perform apoptosis and not necrosis. Necrosis leads to a very strong inflammation, and this is not desirable. Okay, so how we can go around and keep the heating around 43 C and then perform thermal sensitization. We have two ways. We can work on the instrumentation, and of course we need a temperature sensor And we need an electronic control to control the frequency of the AC field, the amplitude of the AC field, and the total time of application of the treatment. On the other hand, possible solution is the magnetic nanoparticle design. So we can play with the phase of the material, with the shape and size of the nanomaterial. So in terms of instrumentation, I would like to call your attention that the same magnet nanoparticle you can use to perform magnetic hyperthermia. Also, you can use as a nano thermometer. So here is a paper showing how you can use the same magnetic nanoparticle to perform magnetic hyperthermia and also to extract the temperature precisely with a precision better than 0.05 C. So in terms of sample design, let me show you one example. In this example, we took a standard magnet nanoparticles, magamite, and then we coat magamite with a thin layer of gold. And actually, we produced two samples. The first sample is a very thin layer of gold, and the second sample, the surface layer was thicker. So we have two samples. In terms of particle size distribution, you can see here on the right-hand side, the upper plot shows the particle size distribution. The histogram, the blue histogram, is the naked magamite nanoparticles. And then with the first coating, the thinner gold layer on top of magamite, you can see the gray particle size distribution here. And you can see that the mean size slightly shift to higher values. And then when we coat with a thicker layer of gold, we can see the red particle size distribution and the red curve, which is even shifted to higher mean particle size. So we can modulate the thickness of the gold layer on top of magamite nanoparticles. Besides, of course, we can modulate the mean size of the core magnetic nanoparticle. Okay, when we perform magnetic hyperthermia with samples, we can, for instance, look at the response, the temperature versus time curve. And on the left-hand side, lower part of my slide, I can show you what is the response when we are using 112 kilohertz AC magnetic field and amplitude of 18 millitesla. And then you can see the response of the three different samples. The blue data shows you the trend, the typical trend of the temperature. But you can see that the asymptotic temperature goes higher than 50 C, which means if you operate this one in a standard magnetic hyperthermia treatment, you are going to perform necrosis. However, if you look at the data with the thinner layer and thicker layer of gold on top, so the temperature, the asymptotic temperature goes below 40 C. So it not even cross the 40 C, and then it's not desirable. Both conditions are not desirable. However, if you take the same samples and change the AC frequency from 112 to 631 kilohertz and lower with the amplitude of the AC field by half from 18 millitesla to 9 millitesla, and then you can check the response. So the uncoated magamite nanoparticles go higher in asymptotic temperature, goes higher than 70 C, which is not desirable. However, the thinner coating gold on top of magamite, the same magamite nanoparticles, it goes exactly in the range which is desirable to perform magnetic hyperthermia in terms of thermal sensitization. So what these two data can show you is that you can manage it to find the combination of parameters, sample plus instrumentation, in such a way that you can work your magnetic hyperthermia effect and set the final asymptotic temperature in the right region to perform apoptosis, which is desirable. So all these curves here, so the temperature dependence, the time dependence of the temperature, it goes with this phenomenological expression called the Box-Lucas, where we have the asymptotic temperature and the heat transferring time, the typical heat transferring time, which is a very important point. Okay, so let me show you a very interesting result from magnetic hyperthermia. It is in the range of a thermal sensitization, actually. So this experiment was reported by the Japanese group. It's a very important data. So here is a rat, a mouse, sorry, and then you can see that it was implanted tumors on both sides of the body, and they record the temperature in the tumor, and this is the lower tumor is the one they injected magnetic nanoparticles, actually magnetite nanoparticles. On the upper tumor, they didn't inject anything, but they recorded the temperature in the upper tumor, in the lower tumor, and in the body. And you can see in the plot here how the temperature goes with the time of application of the AC field in minutes. So they went up to 30 minutes. And you can see that the temperature in the tumor saturates is asymptotic around 45 C. Okay, so they performed the magnetic hyperthermia. This is the frequency of the field they applied, and the amplitude was 380 millitesla. They applied for 30 minutes, like you can see in the plot, and 3 times a day. So the treatment, after 1 month of treatment, you can see both tumors completely removed from the body. So they use about magnetite nanoparticles, about 10 nanometers in diameter, and they use this magnetite inside the cationic liposome. So it's a magnetoliposome treatment. So this is a very important result in the literature, perhaps one of the most intriguing results in the literature in the magnetic hyperthermia used for tumor treatment. Again, let me take the experiment from the German group in Vienna. So here is how they performed. They injected also magnetite nanoparticles in the tumor. The magnetite was about, again, 10 nanometers in diameter, and they were coated with dextran. And so they injected and they applied the magnetic hyperthermia with this frequency, 450 kilohertz and 140 millitesla. And they performed this with 12 minutes in a single treatment. Remember the curve of these, the temperature went, the treatment, the temperature went a little bit over 70 C. And what happened? Completely remission of the tumor. But this was not thermal sensitization, but it was thermal ablation. So what happens with the tumor cells was necrosis, actually. Okay, so let me make a comment about the Box-Lucas model. So actually, the Box-Lucas model has been used for over a decade as a phenomenological expression, but you can extract this expression from the first principles. So let's say you have the magnet nanoparticles in the core. You have a thin layer. It could be a shell layer like metallic, like gold or silver, or it could be the cationic liposome or any coating like dextran. Okay, so the magnetic hyperthermal effect, it applies to the core magnetic nanoparticles. And then it heats up the core magnetic. And then there is a transferring, the heat transferring. And we call this the HS is the thermal current coming out from the magnetic core to the environment. So uh, we can extract, we can correlate the thermal current with the rate of production of heat. So the heat production rate actually is the definition of the thermal current. And then we can scale the thermal current with the thermal conductivity and the area across which the heat is transferring, and the gradient of temperature. So we can manipulate this expression, of course, in this way. If you take a spherical system, and then the area goes with 4 times pi times r square, okay, we can manipulate the expression, and then we can integrate both sides of this expression. So if you take the thermal current is constant, comes out from the integral, and then we can integrate from r, which is the radius of the nanoparticle, up to the external part. If we take the thickness of the layer like E, so we integrate from R to R plus E. So this is the thermal transferring from the core up to the outer layer. And at the same time, we can set the temperature of the core and the temperature of the outer layer. So after integrating this, we can finally comes to the relationship between the rate of the temperature increase as a function of the temperature of the core and the temperature of the external medium. And there is a standard relaxation or transferring time here. And then we solve this equation, which is a very simple solution. It's first order differential equation and non-homogeneous. And solution is exactly the Box-Lucas model. So, and the typical heat transferring time, it depends, very interesting, it depends on the characteristics of the magnetic nanoparticle, because it depends the heat constant of the magnetic nanoparticles, it thermal conductivity of the layer, coating layer. So then we have now not a phenomenological Box-Lucas expression, but a very simple deduction of this one. So let me come to a few important conclusions about my talk. So the first one is that it is possible to preset the temperature in magnetic hyperthermal operation. You can do this just playing with the instrumentation and the characteristics of the magnet nanoparticle you are using. Because of this, it is possible to operate magnetic hyperthermia safely in the clinic. And this is because the a play in terms of material science, a play between the core characteristics and the shell characteristics in the morphology of magnetic nanoparticles, a very promising approach. So, pore, core size, and shell thickness are actually demodulating parameters if you're looking at the material size. On the other hand, AC, magnetic frequency, and amplitude are also modulating parameters, which means a combination of the materials parameters and instrumentation parameters can lead you to write down um, clinically safe protocols for operation of magnetic hyperthermia. And finally, Box-Lucas model is no longer phenomenological. It can extract this from a basic principles of heat transferring. So I'd like again to thank the organizers of this meeting, all of you online attending my talk. And if you have any question, I will be pleased to take the questions. Or alternatively, you can contact me by using my email address. So thank you again for attending the meeting. Thanks again, the organizers of this meeting. Thank you.